And before I start my talk, I would like to thank the organizers, in particular Wilson and Branko, for all the work that they have put into making this conference possible. Of course, it would have been nice to see everyone in person like the previous conferences, but that's the best we can do this year, and I hope Archimedean valued fields and show the connection of non-Archimedean valued fields to other mathematical objects like ultrametric spaces, non-Archimedean ordered fields. And the goal is to get to some special non-Archimedean fields that we work on in my research group, namely the Hahn fields and the Levi-Civita fields. And that will pave the ways to the next talks by Angel and Darren. So here is the plan for my talk. First, I will give a brief review of non-Archimedean valued fields and ultrametric spaces, and show that there is a one-to-one correspondence between the two. Then I will give some special examples of non-Archimedean valued fields. Of course, all the participants here are familiar with the first example, the p-Adic fields. So I will put more emphasis on the others. And I will end with two very special non-Archimedean fields, the Levi-Civita fields R script and C script, and I will tell you what's so unique about these two fields. Okay, so I start with non-Archimedean valued fields. First, we define what we mean by a valued field. So given a field K, evaluation is a map from K to the set of non-negative real numbers that satisfies the following properties, which look like the properties of the absolute value in R and C. So we can think of the valuation as a generalization of the concept of absolute value in R and C. The pair is called a valued field, and for simplicity, we will simply denote it by K. The value group is the set of all valuations of non-zero elements of K. And this is a isomorphic to a subgroup of the multiplicative group of positive real numbers. We say that the field is non-Archimedean, or that the valuation is non-Archimedean, if this set, which is obtained by adding the multiplicative neutral element of K to itself, and we can think of this set as a copy of the natural numbers in the field K. So the field is non-Archimedean if this set is bounded with respect to the valuation. Otherwise, we say that the field is Archimedean. Okay, so that's what we mean by non-Archimedean with respect to evaluation. And the following theorem gives us other equivalent conditions. So the field is non-Archimedean if and only if the valuation satisfies the so-called strong triangle inequality, which is stronger than the usual triangle inequality. If and only if the valuation of A plus B is equal to the maximum whenever A and B have different valuations in K. if and only if the valuation of n times 1 is less than or equal to 1. So this is stronger than the original definition, but the two are equivalent. Okay. And then to get to ultrametric spaces, I will recall what we mean by a metric on a set X. It's a map from X cross X to the set of non-negative real numbers that satisfies the following properties. Delta xy is 0 if and only if x is equal to y. We have the symmetry property and the triangle inequality. Again, this is reminiscent of the distance function in Euclidean space. The pair x delta is called a metric space, and again, for simplicity, we will simply refer to it as x. As in Euclidean spaces, given a point in x and a positive real number r, we can define the closed and open balls centered at A of radius r as follows. And we can use that to define what we mean by an open set as a set in which for every point, we can find a whole ball, open ball around that point contained in U. And the collection of all open sets define a topology on X, which is called the topology induced by delta. The metric is called an ultrametric, and then the space will be an ultrametric space if the metric satisfies a strong triangle inequality. And here we have, again, an equivalent condition for that. So the metric space is an ultrametric space if and only if the metric satisfies the isosceles triangle principle, which is the following. For all x, y, z, if the distance from x to y is different from the distance from y to z, then this is equal to the maximum of the two. So we have equality here if these two are different. And this is called the isosceles triangle principle because if we think of x, y, and z as the vertices of a triangle in the space, then this says that at least two of the sides will always be equal. And here is the correspondence between these two. Whenever we have a valued field, we can use evaluation to define a metric as follows. We define delta of AB to be the valuation of A minus B. And we can show that this is a metric and it induces a topology on K and makes it into a topological field. And then we say that the field is complete if it's complete with respect to this metric that comes from the valuation. Okay. If K is Archimedean and complete, then it's topologically isomorphic to R or C. So all other complete valued fields are non-Archimedean. So almost all but two complete valued fields are non-Archimedean. And we can see from the definition here that if we have a non-Archimedean valued field, which means the valuation satisfies the strong triangle inequality, then in that case, the metric itself will satisfy the strong triangle inequality, and we get an ultrametric. So every non-Archimedean valued field is an ultrametric space. And the converse is true because every ultrametric space can be embedded into a non-Archimedean valued field. So there is a one-to-one correspondence between the two. Here are some of the unusual properties of ultrametric spaces, which all come from the strong triangle inequality of the ultrametric. So given an ultrametric space, every point in a ball is the center of the ball. Each ball is both open and closed in the topological sense. So Kloppen, and has an empty boundary. If we take any two balls, they are either disjoint or one is contained in the other. We cannot just have a simple overlap. Moreover, if the two balls are disjoint, then the distance between them can be obtained as the distance between an arbitrary point x in B1 and an arbitrary point y in B2, which is to say that this distance here is independent of the choice of x in B1 and y in B2. The topology induced by the metric is zero-dimensional, which means that we can find a base of the topology consisting of Kloppen sets, and that entails that the space is totally disconnected, and that leads to many difficulties when we try to do analysis on the space. There are no new values of an ultrametric after completion. So if we have x delta, an ultrametric space, and we take the completion with respect to the metric, then x hat, delta hat, then the values taken by delta hat are the same as the values taken by delta. We don't gain any new values. A sequence in X is Cauchy if and only if the distance between two consecutive terms goes to 0. And that leads to a result that every undergraduate student's dream, that if we have a sequence in a complete ultrametric space, then this infinite sum converges if and only if the underlying sequence AN is a null sequence. In the classical case, of course, we have one direction, this one, but the opposite direction is not always true. Okay. One concept that is very useful in the non-Archimedean or ultrametric context, more useful than Cauchy completeness, is spherical completeness. An ultrametric space is called spherically complete if each nested sequence of balls has a non-empty intersection. And this concept plays a key role in for the validity of the Hahn-Banach theorem in the non-Archimedean context. We need spherical completeness for the Hahn-Banach theorem to work. And if you look closely at the definition, you can see that spherical completeness implies Cauchy completeness, but the converse is not true. However, the following result gives us a partial converse. So if we have a Cauchy complete ultrametric space, and if 0 is the only accumulation point for the metric or the ultrametric in this case, then the space is spherically complete. So only in that case, we can for sure say that Cauchy completeness implies spherical completeness. There are two important attributes for spherically complete ultrametric spaces besides the Hahn-Banach theorem. for ultrametric spaces, we have spherically complete ultrametric spaces. We have a stronger version of the fixed point theorem, which says every shrinking map of a spherically complete ultrametric space has a unique fixed point. In the classical case, we need the map to be contracting, not just shrinking. So this is a weaker condition for the fixed point theorem to work. And existence of best approximations. So if Y is a non-empty, spherically complete ultrametric space embedded in another ultrametric space X, then every X in X has a best approximation in Y, which means that the minimum of delta YX for Y in Y exists. Okay, this is not true in the classical case. And it's worth noting here that best approximations are not, in general, unique. So each X may have infinitely many such Ys that are best approximations. Okay, and now we get to the examples. As I said, people in this group are very familiar with the p-Adic fields. So I will skip these two slides in the interest of time and go to ordered fields. Given an ordered field K, then for non-zero element X and Y, we say that X and Y are comparable if we can find non-negative integers N and M such that ny0 exceeds x0 and mx0 exceeds y0, where a0 is the usual absolute value, which is equal to a when a is non-negative and minus a is if a is negative. And this defines an equivalence relation on K star. The equivalence class of X will be denoted with square brackets, and the set of all equivalence classes, also known as Archimedean classes, is denoted by GK. GK is an ordered abelian group under the following order relation and addition, defined as follows. We say that X, the class of X, is smaller than the class of Y if and only if and Y0 is less than X0 for all N. And in this case, we say that Y is infinitely smaller than X. And we define addition of classes as a class of the multiplication. The neutral element with respect to this addition in GK is the class of 1K, the neutral element for multiplication. And the additive inverse of the class of X is the class of X inverse for X in K star. Okay. And now we say that the ordered field is Archimedean if there is only one Archimedean class. So GK is a singleton. And this means all non-zero elements of the field are comparable. Each ordered Archimedean field can be embedded in R. So R, we can think of R as the maximum Archimedean ordered field. Now, Hahn in 1907 generalized this property of the reals to other ordered fields, and he ended up with ordered fields that extended all other ordered fields of the same level of non-Archimedicity, and I will explain what that means. Okay, so he ended up with an ordered fields that are maximal in the same sense as R is maximal for Archimedean ordered fields. Okay, so let E slash K be an extension of ordered fields. Then we say that E is an Archimedean extension of K if every element in X in E is comparable to some Y in K. Okay, and in this case, GE and GK will be isomorphic ordered groups. An ordered field K is called Archimedean complete if it has no proper Archimedean extension fields. So we cannot extend it any further with another ordered field that is an Archimedean extension of the original field. Okay, and here's a definition. Given an ordered field K, if G is an ordered abelian group that is isomorphic to GK, recall GK is the set of Archimedean classes or equivalence classes under the relation comparable. Then we say that K is of type G, or G is called an Archimedean group of K. The simplest Archimedean complete ordered field is R. Since it's up to isomorphism, the only Archimedean complete ordered field of type 0. Okay. So this is the maximal ordered field where all non-zero elements are comparable. Now Hahn generalized that to other non-Archimedean ordered fields, and he obtained Archimedean complete fields of other types. And these are called general Hahn fields, which I will discuss next. So given any field K, not necessarily ordered, and G an ordered abelian group, then the set of all maps from G to K with well-ordered support, where the support is a set of all points where the function is not 0. This is a field under the following addition and multiplication, addition component-wise, and multiplication as a convolution. Such fields are called general Hahn fields. If K happens to be an ordered field, then we can introduce an order on the field, the general Hahn fields K of G as follows. First, we define lambda of F for any non-zero elements of the field as the minimum of the support. This exists because the support is well ordered. So any a proper subset of this has a least element. In particular, any subset of the support has a least element. In particular, the support itself has a least element. We call this lambda of F. And then if we take two elements of the field, we say that F is less than G, if and only if they are different, and F minus G at the minimum support is negative. So what does that mean? If F is not equal to G, we look at the first point where the two are different. If F is smaller than G at that minimum support, then we say that F is less than G. So we have a lexicographic order from left to right. Then with respect to this order, K of G is a totally ordered field. And the following two results give us the two main features of the general Hahn fields as ordered fields. And they mimic the relation between R and other ordered Archimedean fields. That's what I hinted at earlier. The first one is the Hahn embedding theorem, which says the following. If K is an ordered field, then for every Archimedean group G of K, we can find an order preserving field monomorphism, sigma, from K into the general Hahn field R of G, such that R of G is an Archimedean extension of sigma of K. So what this says, if you have an ordered field of type G, you can embed it into the general Hahn field R of G. Okay. Like you can embed any Archimedean ordered field in R. And the next one is the Hahn's completeness theorem, which says that R of G is up to isomorphism, the only Archimedean complete ordered field of type G for any ordered abelian group G. Okay, so this is similar to saying that R is the only Archimedean complete ordered field of type 0. Okay. So the general Hahn fields play the same role in the non-Archimedean ordered fields that R plays with respect to ordered Archimedean fields. Now, a Hahn field is one special general Hahn field for which G is a subgroup of R plus. And in this case, because G is a subgroup of R, we can define evaluation on a Hahn field as follows. The valuation of F is E minus lambda of F. Remember, this is the minimum of the support if F is not 0. And we define this to be 0 if F is equal to 0. And it's easy to check that this is a non-Archimedean valuation. And the field becomes a spherically complete, non-Archimedean valued field with residue class field isomorphic to K and the value to the group of the form EG, G and G. So with respect to this valuation, the Hahn fields are always spherically complete. As subfields of the Hahn fields, we define the following fields. Instead of having well-ordered support, we take the maps that have left finite support, which means below every integer, there are only finitely many points in the support. So the collection of all such maps forms a subfield of the Hahn field K of G. Such fields are called Levi-Civita fields. And when we restrict the valuation of K of G to the Levi-Civita field L of GK, then we obtain a Cauchy complete, in general not spherically complete, non-Archimedean valued field, again with residue class field isomorphic to K and value group of the form EG, G in K. given a field K and this map D from Q to K defined by D of X equal 1 if X equal 1 and 0 if X is not equal to 1. So this is a map that has only one support point at X equal 1. Then D is an element of the Levi-Civita field L of QK. And for any R, dr of X is given by this, 1 at if X equal R, and 0 if X is different from R. This is also an element of the Levi-Civita field. Moreover, this function or element of the Levi-Civita field plays the role of generator. So every non-zero element F of the Levi-Civita field can be written as a generalized power series of this form, which converges with respect to the valuation on the Levi-Civita field. Okay. Because of the left finiteness of the support of the elements of the Levi-Civita field, this always converges with respect to this valuation or with respect to the ultrametric that we obtained from the valuation. Okay, and the following result tells us exactly when the two fields, the Hahn field and the Levi-Civita field, are equal or coincide. The two coincide if and only if G is discrete, if and only if the Levi-Civita field itself is spherically complete. Okay. Moreover, if K is an ordered field, then the Hahn field is an Archimedean extension of the Levi-Civita field with respect to the order. Remember, if K is ordered, we can introduce an order on the Hahn field, and therefore we use the same order on the Levi-Civita field, which is a subfield of that. If in addition K is Archimedean, then both of these fields are of type G. Some general Hahn fields are real closed. I will say exactly when we can assure this is the case. If K is any field and G an ordered abelian group, then the general Hahn field is real closed if and only if K itself is real closed and G is divisible. The Levi-Civita field L of QK is real closed if and only if K is real closed. And this entails that the Hahn field R of Q and the Levi-Civita field L of QR are real closed because of these two results. And this in turn entails that the complex versions of these fields, namely the Hahn field R of Q of I, this is the imaginary unit, which is the same as C of Q, replacing R by C, and the Levi-Civita field L of Q of R of I, which is the same as L of Q of C, replacing R by C in this field, are algebraically closed. It is these two Levi-Civita fields, L of Q of R and L of Q of C, that have been the focus of the research in my group because they are unique and I will tell you how they are unique. So for the remaining 10 or 15 minutes, I will focus my attention on these two fields. But maybe at this point, I will pause to ask if there are any questions. Okay, then I will continue. So I will denote by R script the Levi-Civita fields, L of Q and R. Remember, this is the set of all maps from Q to R with left finite support. And C script is L of QC. Again, the set of all maps from Q to C with left finite support. It turns out that R script is the smallest Cauchy complete and real closed non-Archimedean field extension of R. In fact, this is small enough for the numbers to be implemented on a computer and to allow computational applications. And C script is the smallest Cauchy complete and algebraically closed non-Archimedean field extension of C. So these two fields are special from a pure mathematical point of view because they are the smallest non-Archimedean extensions of R and C with these special properties. And they are also special from a computational point of view because we can use them on a computer. And that's what motivated me when I was a graduate student a long time ago to work on these fields. So here I will list some of the research work on the Levi-Civita fields. We did study the topological structures of the fields, both in the evaluation topology and in a weaker topology, which is generated by a family of seminorms. And this weaker topology allowed for the extension of a real power series into the Levi-Civita fields. Real power series do not converge with respect to the evaluation topology. So we had to introduce a weaker topology. Then we studied in details power series and analytic functions on these fields. And we showed that these behave as nicely as real and complex power series. We succeeded in extending all the useful calculus theorems on R to R script with mild conditions. We did Lebesgue-like measure theory and integration on R script 2 and R script 3. Darren later today will talk a little bit about this. We did some optimization, operator theory. Angel in the next talk will talk a little bit about that. And we did some computational applications. One such application I will talk about next, and Darren will also talk in his talk later about some other applications. At the end of this talk, I will provide a link to papers on all these research topics. But for now, let me present this nice application, which was the first paper I did on this field and which triggered my interest in the Levi-Civita field, but then I focused more on the pure mathematics aspect of it. So this application was computation of derivatives of functions that we can represent on real valued functions that we can represent on a computer. The need for differentiation tools arises in many fields of science and engineering. And while formula manipulators like Mathematica and Maple, for example, are successful, they do not always work. For example, if we take this function, which is easily seen to be differentiable at 0, if we try to compute the derivative using Mathematica, this may fail if the programmer doesn't do their job right because of the existence of a non-differentiable part, namely the absolute value. So using the calculus on R script, we formulated a necessary and sufficient condition for the derivatives of a function representable on a computer to exist. And we showed how to find all those derivatives whenever they exist. So let me define formally what I mean by a computer function. A computer function is a real valued function that is obtained from the intrinsic functions and the Heaviside function or step function through a finite number of arithmetic operations and compositions. So this is a formal definition. In a casual way, what this means, a computer function is any function you can type on a computer. Since intrinsic functions are given by power series or root functions, all of these have been generated, have been generalized from R to R script. So the computer functions have been extended to R script. Then we define now what we mean by an extendable function to an R script number. So given a computer function f and x0, a point of a real value, real point of its domain, and s an R script number, then we say that f is extendable to x0 plus s if x0 plus s is in the domain of f bar, which is the continuation of f to R script, which exists because of what I said. Okay. We have derived a standard form for all computer functions. Given a real computer function, a point x0 of its domain, and assuming that f is extendable to x0 plus or minus d, then there exists a positive real number sigma, such that in the sigma neighborhood of x0, the function is given by this form. So this applies to any computer function that can be extended to x0 plus or minus d, where the a0 and ai's are all power series. The qi's are rational numbers that are not zero or positive integers. These may come from root functions here. Okay. And we use this standard form to derive our necessary and sufficient conditions in an iterative way. So first, f, we check that f is defined at x0. Like here, f is defined at x0 if and only if f of x0 can be evaluated on a computer. So that's the first thing we do. We make sure that the function is defined at x0. Then, having checked that x0 is a point of the domain of the function, then f is extendable to x0 plus or minus d, if and only if the continuation function, f bar, can be evaluated at x0 plus or minus d on the computer. Okay. Now, having checked that f is defined at x0 and x0 plus or minus d, the next step is to check for continuity. The function is continuous if and only if f bar at x0 minus d and f bar at x0 plus d are both at most finite, and the real parts are equal to f at x0. This notation here means up to the zeros power of t. So both of these have no negative power of t. This means they are finite, and the zeros zeros power term in both of them has to be equal to f of x0. So in other words, the function will be continuous if and only if this is of the form f of x0 plus some infinitely small correction, and the same for this one. Now, having checked continuity, we move to checking differentiability, and we can do that up to any order in one step. So f will be m times differentiable if and only if up to the mth power of t, f bar of x0 minus t and f bar of x0 plus t are given by this, where for each j, aj plus is minus 1 to the j, aj minus. So in other words, if we cut the expansion up at the mth power of d, there are no non-integer powers of t. The even coefficients will be equal, and the odd coefficients will be opposite to each other. And in this case, the j's derivative will be j factorial times aj plus for all j from 1 to m. We used that algorithm to compute the first 10 derivatives of this rather ugly function. And we ended up with this table. To make sure we got the correct answers, of course, we had to check this against the values computed with Mathematica. And if you look at these two tables, you see that for f at 0 and the first 5 derivatives, the values agree up to the 16th digit, but Mathematica, of course, took much longer. For the first derivative, almost 100 times longer. For the fifth derivative, 7,000 times longer. And this is understandable because Mathematica has to first compute the derivatives analytically and then substitute the value 0 to get the numerical values for the derivatives. Okay, so with using the existence of infinitely small numbers and the fact that the Levi-Civita numbers can be used on the computer, we achieved the accuracy of Mathematica, but the speed of classical numerical methods. So the best of both worlds. Here is a link, the promised link for papers that have been covered in this survey talk. There you will find a survey paper on non-Archimedean valued fields in general, and papers on specific research topics like power series and analytic functions, operator theory, and so on. And with this, I thank you for your attention. Any questions? Any comments?
Thanks very much.
Anta?
Could you please solve the first page?
Oh, I can.
Yeah.
You're muted, I think, Anta. I can't hear you.
Yeah, I would like to see the second page. Can you hear me?
Just a second.
Or maybe I can chat.
Try now, please.
Yeah, so could you please solve the second page?
Uh,
I want to know why do you need the condition K1 is not infinity?
Which slide are you referring to? Or which part?
That's the beginning.
Yeah.
Yeah.
At the beginning, so let me see. Okay.
So
where? Here?
next.
Yeah. Tell me where. Here?
Yeah.
Okay.
So why do you need the condition this one?
This one?
Not
Yeah,
infinity?
this is, yeah, that's what makes the valuation non-Archimedean. This is not true, of course, in R and C. That's why they are Archimedean.
Oh, okay. Yeah.
Yeah, so this is equivalent to the strong triangular inequality for the valuation.
Oh, I see. Yeah.
Yeah, so that's what distinguishes a non-Archimedean valued field from an Archimedean valued field, this condition here.
Okay, yeah, thank you. At first, I thought that mean characteristic is not zero. So this is not related to characteristic of field?
Yeah, that's different. I mean, you have non-Archimedean valued fields of different characteristics.
Yeah, okay, yeah, I see, yeah.
Yeah.
Okay, thank you.
You're welcome. Any other?
Professor? Yes, hi, Professor. Thank you for your talk.
You're welcome.
I just I wanted to make a small precision. But when you mentioned that there is a correspondence, one-to-one correspondence between non-Archimedean value fields and ultrametric spaces, well, this is not like that. I mean, if you consider a non-Archimedean value field and you consider proper subspaces that doesn't have any kind of structure like scattered points, and you equip them with the metric induced by the valuation, then you will have ultrametric spaces as well, right? So yes, we can, every non-Archimedean value field is an ultrametric space. Yes, every ultrametric space can be embedded into a non-Archimedean value field, but that embedding not necessarily is surjective. So because So in other words, not every ultrametric space necessarily will have the algebraic structure of
sure. Yeah. I meant that you can embed it. So there is that relation. Yeah. Okay.
Yeah,
Thank
this
you.
is more clarification. Yeah.
Yes. Any other questions or comments? All right. So in that case, I think we have a 5 minutes break before the next talk by Angel.